Hello, this is Jennifer Martinez, and in this video we're going to talk about new functions from old. And the first thing we're going to look at is shifts and stretches. So let's start with some stretching. So if you have this function, the function you'll see is on the dotted line here. If you have just an arbitrary function and you take 3 times that function, it is easy to see that the graph of a constant multiple of a given function is stretched. It just means we're going to take 3 times each of these y values. So we have this y value here, and we're going to multiply it by 3, and we get, maybe this is like, I don't know, -1. So -1 times 3 is -3. 0 times the value is still 0. Here, the dotted line is 1, and then the blue line is 1 times 3. Again, 0 times 0 is just 0. And the same thing here. -1 is a -3, and the same thing here. This is about a 1, and now it's a 3. If you take a negative number times the original, -2, it stretches it by a factor of -2. So what ends up happening, it reflects along the x-axis. So if you take 1 and you multiply -1 and multiply it by -2, you get a +2. And then the same thing here. Take 1 times -2, you get a -2, so it reflects it. So looking at the gray line versus the dotted, so here the dotted line is -1, multiplied by -2, it's 2. And then the same thing here, the dotted line is 1, and multiplied by -2, you get the gray line. So it reflects it. If you look at the whole graph, it flips it, reflects around the x-axis. What about the function 1/2 of f of x? What does that do? Well, that's going to shrink it. See, if you look at the original f of x, the dotted line, and you take 1/2 of 1, you would get this line right here. And then if you, 0 times 0 is still 0. If you take the dotted line here at 1 and you multiply that by 1/2, you would get about like that. And then the same on this side. If you take half of -1, you get -1/2. 0 is still 0. And finally, if you look half of 1, again, it's 1/2. So you can see that this line gets shrunk by 1/2. It shrinks it. Okay, so now let's look at some shifts. Let's start with this example. So if you take y equals x squared, a specific function, and you add 4 to it, you can see that it would just shift it up 4. Everything would be raised 4. That would make sense. Easy to see. So in general, if I let y equal f of x, in our case, f of x is equal to x squared. So I'm going to let the y equal f of x, which is x squared. And we saw that if we added 4 to it, you get a shift up. So in general, what is that? That's f of x plus 4. So adding 4 to your original function shifts up or down. If it's negative, it would shift down. So if you had x squared minus 1, you would expect it to shift down. And that would make sense, because that would just be x squared minus 1. So 0, we would subtract 1 there, and we would end up with a shift down everywhere of -1. The actual shape doesn't change, and it does not get stretched. It just shifts everything down 1. What about a horizontal shift? Notice how this looks like a horizontal shift. Instead of the number being on the outside, now it's on the inside. So if we take this x squared and we subtract 2 on the inside, it actually is a shift 2 to the right. It does make sense because when x is 2, y is 0 there. So it does the opposite sign because it's within the function. Again, I'm going to let y equal f of x, and we know that therefore f of x is x squared. If you look at this would be f of x minus 2. And f of x minus 2, if I plug that in here, would be x minus 2 squared. And it would be a shift to the right. Again, plugging in a 1 here. On this one, actually 1 on this one would be like plugging in a 3 on this one. A little more tricky. So that is why in general, what we're going to do here is they like to, I'll just look at the shifts first. This is in general. By replacing y by y minus k, it moves it up or down. Down if k is negative. And replacing x minus h moves the graph to the right by h, and h if it's negative. So it makes it the opposite sign. So on this one, how they like to think about this is instead of this, they like to think of it like this. And so then they'll both be the opposite sign. This will move it up 4 instead of the way that we originally did. And then multiplying, we already saw this, by a constant c stretches vertically if c is bigger than 1, or shrinks it if it's between 0 and -1. A negative sign reflects across the x-axis, in addition to shrinking or stretching. Composite functions. What is a composite function? It's a function within a function. So let's look at this example to check out composite functions. Example 1. So we still have f of x equals x squared, but now we have g of x equals x minus 2. Let's find the following. So I'm going to start with part A. So how to find the value of a function within a function is you always do the inside function first. So I'm just going to say since g of 3, if I look at g of 3, we know it is 1. So I'm going to say this is f of g of 3, which is 1. And then I'm just going to find f of 1 normally, and it's also 1. You can see this is different than the other way around because this one you have to find the f. So I'll just do that over here. F of 3 first. So if you look at f of 3, you're going to plug it into the first one, which is 9. 3 squared is 9. So this would be g of 9, which g of 9 would be 9 minus 2, which is 7. So you can see that they're different. They're not commutative. So in general, if you do it with x, f of g of x, what would that look like? Is instead of figuring out the g of x first, we're going to look at f of the g of x. So it'll just be, it's going to be a shift to the right. So it's going to be x minus 2 squared. The other way around, what is g of f of x? That is going to be, again, g, doing this first, putting this in here, it would be g of x squared. What would that be? That would be something totally different than a shift. That would just change the function to x squared minus 2, because now I'm going to put x squared in for the x there. It becomes a parabola where it originally was a line. So let's try this example. You can practice this on your own if you want, and then come back to see the answer. Here's the solution. Plugging in a 2 plus h into the original, you end up with the following: h squared plus 6h plus 11. G of 2, that's just plugging in a 2. So the answer should be 11. And then part C, plugging in a 2 plus h, and then subtracting a g of 2, you would get the part A minus part B. So you would end up with just h squared plus 6h. What does that mean? Yes, if I graph the original with this is a shift to the left and then to the left 2 and then down 11 because g of 2 is 11. Let's look at that. There's the first one. Left 2, yep, and down 11. But I'm going to look at this a different way. Since this is an h, I'm going to think of this as a point. So I'm going to just use my first function, and then I'm going to change my window to make sure that it sees 11. So I decided to choose this as my window. And I'm going to go to graph that. Let me copy that and paste it on my page so I can work with it. I'm going to start with part B because now we're just working with points. G of 2 is 11, somewhere right there because the top was 15. That makes sense. G of 2 plus h, I don't know what h is. So this is 2, so I'll just make 2 plus h some arbitrary amount. You can see that this would be g of 2 plus h. Would say this is h, that distance. And so g of 2 plus h minus g of 2 is just this distance right there. That is g of 2 plus h minus g of 2, right? Because that is the g of 2 plus h, that is g of 2. And that's assuming this is if h is positive. If h is negative, it would just be on the left. Notice it almost looks like the rise. If we divide it by the run, if we divide it by h, it is the slope. So we're going to see that in the next chapter. And there it is. So this is the change in y. And the slope of the line between these 2 points, where h is positive, is that delta y that we just found over delta x. And the delta x is really, right, just h, because 2 plus h minus 2 is the delta x, which is just h. Interesting. But we'll talk more about that in the future. And that concludes this problem. Notice how I thought of this again with a particular h instead of 2 different functions. I thought of h as a point and stuck with my original and looked to see what that looks like. Again, we did see that it was a shift if you made this an x and compared those 2 functions. So just 2 different ways of looking at that. Hope this helps. See you next time.